to do the same type of thing. But all that aside is, okay, we have all these buildings, but how many are really at risk of collapse? Lots of damage is expected, but we may not be able to economically protect all of these buildings against damage. All buildings get damaged in earthquakes, and since these buildings tend to have a few more zeros on the retrofit cost than a URM or something of that nature, looking for the ones, again, that are true killers and trying to understand the magnitude of the problem was kind of the focus of what I did. So what I did is pour over previous EERI, earthquake spectra reconnaissance reports, other papers I could find, looking at large magnitude earthquakes to look at the damage statistics that were associated with them. Now, again, this is not very scientific, and I'll kind of preface this all by you'll see earthquakes that are obviously in countries that may not build to the same standards as we do. There's earthquakes that had different soil conditions. When I get into Mexico City, obviously that's not the same thing as here, but just understanding kind of numbers-wise, even given their conditions, you know, what type of damage did they see? Different eras of construction and so forth. So all that kind of prefacing what I'm going to show, but again, I wanted to kind of find as much data as I could just related to reinforced concrete design. So I'll show a few slides here from earthquake statistics that I have, and know that these are all just reinforced concrete. So when I talk about percentages and so forth, it's just relative to similar buildings. And all other building types are kind of out the window, so to speak. So starting off, you know, the first paper you get to is kind of the Niigata magnitude 7.5. Nearly all of the damage here was due to liquefaction. So you can't really say it's going to be the same type of thing, but just looking at that, about 2/3 of the buildings were damaged due to foundation issues, but you kind of look at overall how many were damaged. Only about 21% of the buildings were actually even damaged in that event. So pretty big event. It's not talking about shaking. I know we're talking just magnitude here, not spectral accelerations or distance from the event, the main epicenter and so forth, but just getting an idea overall of damage statistics. About 21% of the buildings were damaged. So seemingly the ones that collapsed are the ones that kind of had that slow lean due to the liquefaction, so maybe not directly applicable to what we're studying here. Moving on to Venezuela, 67. They had about 1,000 buildings, 10 stories or taller, and only 5 major collapses were seen in that event. There was some reconnaissance reports done on that one. A lot of the damage and collapse issues were related to, again, overstress of the column elements. Also, those buildings, they were designed by assuming all the frames in the building took the same amount of load, essentially, based on the stiffness of the frame, but then they infill certain exterior ones and a couple of interior ones, so those frames obviously are going to take more load, more overturning loads getting into the columns and so forth. Other things that we've seen before, insufficient ties in columns, obviously, and so forth. Inadequate joist reinforcing in some of these flat slab type of conditions. They had a lot of the joist systems, one-way joist systems, and not sufficient continuous reinforcing, causing some issues. Again, but when you look at the numbers, 5 out of 1,000 that are 10, that large is not a big number, but it's a high consequence number. 1968, Off-Tokachi, magnitude 7.9. These authors used terminology that I don't know exactly how to interpret, but they used completely destroyed, mostly destroyed, half destroyed, or undamaged. So if we kind of squint and say completely destroyed and mostly destroyed, or these are probably collapses, we can agree on that. Mostly destroyed, maybe half of those are collapses, that sort of thing, but you're starting to get in the area of maybe 10 to 15% or so collapse. These older events kind of tell us a little bit because they're definitely pre-earthquake code, as I will say, for reinforced concrete. So Japan in about 1971 started transitioning to more and more strict regulations on their concrete building code. 81 is kind of our equivalent to 76 or so in generic terms. So some of these are kind of affecting buildings that we're thinking about as well, unlike some of the newer earthquakes maybe. 1978, Off-Miyagi, another big earthquake, magnitude 7.4, using that same terminology of completely destroyed, mostly destroyed, half destroyed, and so forth. There again, lower percentages, 2 to 5%, 2%, maybe adding up those first two, mostly and completely is 7%. Again, but it's not this huge number. If people are used to kind of thinking in terms of the P695 definition of 10% chance of collapse in an MCE, these may not be MCEs, but these are old buildings and probably perform a lot worse than a newer building, so that 10% is probably a gross exaggeration of what we would truly expect. But again, just kind of blinding, putting on the blinders and just looking at the damage, this is what I was seeing. Mexico City, magnitude 8.1. Craig showed earlier in this morning a little graph, a bar chart from the data from Otani, the research from Otani. I'm going to show a little bit more deep dive on a couple of those parameters here. So in Mexico City, he and a team looked at the two most affected regions with respect to reinforced concrete building damageability. And in those regions, one being the lake bed region, you can imagine higher, taller buildings are affected more strongly there due to the period of the soil conditions affecting taller buildings. So it may not be a direct statistic, but it does point to some kind of general numbers. Most 93% were operational of all reinforced concrete buildings. Only 2% collapsed. So again, not a lot of collapses given the great number of these buildings probably built. They could be better, could be worse than our pre-1976 stock. It's kind of all over the map. Breaking that down a little bit further and looking at the effect of stories, the number of stories on that data. I realize you can't really read this, but when you download it, you can see this is actually the data that's in the paper. So I just reprinted it there. So if you want to look at it. So by number of stories, they talk about operational, heavy, or collapse damage. On these bar charts, I didn't even print operational because it would have dominated the scale so much you wouldn't have been able to make out the other ones. So, collapse in the 1 to 3 story range, very small percentage. For one story, there was, one collapse out of over 700 buildings. So again, now as we know that all buildings can be a risk, but there's limited dollars, limited appetite for communities to go after these buildings and do anything about them. In the overall scheme, it starts to, once you look at this data, maybe point to the fact that the shorter buildings are not where the priority should be, the dollars should be focused potentially on this issue. And then as you get to the taller buildings, again, lots of damage, but again, it's a lot of this has to do with the effect of the soil basin, and it's a drained swamp, and this is just the predominant period of the earthquake. Just happens to match the buildings in this zone, so maybe not the best direct comparison. An area that's not as strongly affected by the soil conditions here, same thing, Mexico City. Not a lot of tall buildings, but you see the shorter buildings, no collapses in one story. One collapse out of 71 two-story buildings. When you start relatively looking at the heavy damage, it's really pointing towards mid-rise buildings that were suffering the heaviest effect, and if you want to kind of go after it, maybe that's where you focus things. 1990, Luzon, magnitude 7.7. Overall, again, this is all building heights combined. Only 5% collapsed. And then if you start looking at by number of stories, again, you see relatively small percentages of collapsed buildings. There's no collapses here. I'm sorry because of the color change. On this one, the gray is actually the collapse, heavy damage, and operational. So no damage, again, no collapses again to low one-story buildings. Once you get up to 2, there was a couple. Again, though, it kind of points to the fact that it seemingly would be that the low-rise are less of a problem. Again, I do realize that one of the pictures that Craig showed of LA was a 2-story building, and that was one of the ones that collapsed, but that was 1 of 6, so maybe 16%. Given the amount of those low-rise buildings, it's probably, again, a low percentage of the overall number. Chile, I didn't have any exact numbers of how many buildings there were that performed really well, but if you kind of look at 400 buildings in the immediate zone from the 85 earthquake of 5 to 23 stories, very few collapsed. Only about 5 in this class out of 400 in that range of buildings. So again, really low damage statistics. Erzincan, now again, this is Turkey, and you can't really say it's the same kind of building type. We don't have a lot of hollow clay tile infill buildings. We have a lot of URM infill concrete frames and so forth. So again, not a direct comparison, but again, looking at it, 1 and 2 story buildings not collapsing. It wasn't till you got to 4 or higher, which seemingly points to maybe it's a gravity effect like we've been talking about. Taller buildings just going to have more P delta, more gravity effect on the columns and so forth. Kobe 1995 is the first set of Otani data that talked about pre-code, if you will. So he was able to look at ages of building because he was able to obtain that. So again, pre-1971 is kind of their pre-seismic code for reinforced concrete. Not totally, but and then in this era, the code got a little bit more restrictive and then a little bit more restrictive even still. So you see, not a great variation in the number of collapses, but there's a whole lot more buildings built in these other eras. So low percentages of collapse, and obviously the codes are helping them to improve things in that case. Looking at number of stories, again, kind of the same kind of picture. You see for 1-story buildings, mostly everything is operational, no collapses, and these are pre-1971 buildings even. Again, with more collapses happening in the taller domain. These are post-1981, so once they improved their seismic codes, again, you're seeing these low levels of collapse and heavy damage in the shorter buildings. Soft story damage, they also did break out how many of these, how much the damage was affected by having an open front soft story. And you could see that the damage level was pretty, there was a lot of those buildings that fell into that category. San Francisco and Los Angeles, we've undergone the wood soft story things, which is a great kind of first step. But concrete buildings obviously have the same kind of issues, and hopefully the 78 methodology will bear that out as we go through that. Again, this is just a few more slides, not so important, but looking at the low numbers, Duce 7.4, only 6% of the buildings collapsed. Taiwan, I couldn't find a good number of how many buildings performed well. And that's a big issue we have, is to understanding the magnitude of these events, or the consequence of these events is almost as important as which ones do poorly, is how many did well. So I know I suffered the same thing. You go to a post-earthquake scenario, a week after the earthquake, and you're like, I want to go see that one because that one collapsed. I want to go see that one because that one collapsed. And you kind of walk by 50 that performed well, and you don't take any inventory of how many there were, how big they were, why you think they might have performed well, and so forth. So that's a really important missing piece of data for these. This is not so important in India. I don't think it's really directly applicable, but again, thousands of these buildings, they had 120 of them collapse, even at great distance. Chile, that I know Professor Maley visited, as probably many of these other events, but 80 multi-story buildings with extensive damage, but I believe it was out of a population of about 10,000 buildings that fell into that category, and only 4 buildings collapsed or partially collapsed. And many of these buildings were actually relatively newer buildings, if I understand correctly, that Chile after 1985, and Jack, you may correct me if I'm wrong, in 85 they saw that wall buildings performed pretty darn well. And so actually they kind of lifted some of the restrictions on boundary zone detailing of the walls in subsequent code sections, or subsequent code years. And then this earthquake came along and kind of damaged some of those newer buildings that were built under those newer codes that were actually less restrictive when it came to boundary zones than previous codes had been. So there could be a kind of a going backwards in performance on that. Christchurch, and I'll kind of tie this into a little bit of what we talked about earlier, as to the question of which buildings are important. As was said earlier, lots and lots of URMs disintegrated, collapsed, and so forth. Only 40 deaths attributed to those great numbers of collapses. If you're looking at death as the kind of the performance measure, if you will, the consequence thing. And the two major concrete buildings that collapsed, the Pine Gold and the CTV building, that was around 140 deaths or so for. So attributed to just those two buildings, the consequence of damage to those two buildings was much higher than all the URMs put together times some other factor. The other thing is that there was lots of near collapses, I would say. Here's a wall buckling in the hotel that many are familiar with. This was columns underneath discontinuous shear walls in the Copthorne Hotel. This was the Parkview Terrace Apartments, I believe. So getting kind of near the end of its capacity, maybe. This is the Holmes Consulting Engineering. Two buildings that collapsed, and the one parking garage that was a post-tension flat slab building that had the punching shear failure over on the right. And so what Jack said earlier, that sometimes tendons help you, sometimes they don't. A lot of these columns still had all the tendons kind of rolling over it, and they would snap off. And so they didn't necessarily provide the catenary action that we would have hoped in all cases, but kind of looking at that system already, you're kind of like, ugh, I don't know if I'd want to be there when the earthquake went off. And tying this into kind of my next statement about consequence of damage is, if we look, for instance, at the Northridge earthquake aftermath, what came after the Northridge earthquake? There was some soft story residential type of talk and worry about that, but it was, look at all these steel moment connections that failed, and then look at all the effort that went into the engineering community and research community into addressing pre-Northridge steel moment connections. Well, that's great, and it is an issue, but how many buildings did that actually lead to collapse in, and how many fatalities were a result of that? If this earthquake in Northridge had been at 12 noon, say, on a work day, the whole emphasis most likely would have shifted. The Kaiser concrete building that collapsed and lost a story that you saw there, no one was really in that building because it was in the middle of the night. The parking garage at Northridge campus, who was in there at that time? If it had been full of students at that time, look what would have happened. So you start to look at those things. The Bullock's department store, if that was during shopping hours, look what the fatalities would have been in something that lost a floor. So just by luck of time of day, concrete buildings were unoccupied, and so that kind of went out the window. If that earthquake was at noon, and hundreds, if not thousands of people could have lost their lives from these concrete buildings, who's to say that wouldn't have jumped to the forefront, and probably is something we need to study. So this is kind of the end of the slides on, kind of statistics, but just when we talk about prioritization, it really seems that this is still a class of buildings that we should be concerned about. We see low numbers of them, but they're really high consequence. And as Craig said, many of them are very big buildings, so we should maybe be looking at those first and prioritizing our efforts towards those. The other thing we're going to try and do is do a few more HAZAS types of studies based on the time of loading, meaning how people are in and out of the buildings over time. So maybe it makes sense to focus more on residential versus a building that's used for business, when the business side of things may only be in there 9 hours a day, but in a residential, you may have high occupant load 12 to 15 hours a day. So if these two buildings are kind of created equal, if it's the same building here and here, it seems kind of just on a time and kind of probability of consequence to health that you should be looking at buildings more based on how long they're occupied and the total occupant load. So that's kind of the end of what I wanted to show, and just kind of talk about some of the things that we're trying to do to better, to help fill out data, to help move this effort forward, to understand how big the problem is. So we're continuing to work with different communities, like we said, to do these surveys, and then trying to find better information to fill out type of, maybe there's some intermediate screening that they can do that's not a full ATC 78, but you can start to fill out some of the things that go into an ATC 78 type of evaluation. Have an engineer for $5,000 look at the drawings and say, yes, it has walls. Just a few of the real basic things that have been shown to be big red flags. So that there might be some intermediate step we can go to start kind of at least chip away at the problem a little bit. Other things that is happening in the California area that we're doing is San Francisco has a mandatory seismic evaluation requirement for all private schools. So all private schools, not public, but all private schools are having to do a mandatory evaluation, kind of a tier 1 checklist type of approach to look at their buildings. No retrofits required, but if you are the principal of one of these buildings and you get a seismic evaluation report that's submitted to the city that says you're a high hazard, that's another thing that's kind of pushing some of these buildings to be looked at. And what's kind of important about that for San Francisco in what we're doing is I've looked at 39 buildings so far, and 22 of them are pre-1976 concrete buildings with lots of school children in them. So we're starting to get an idea of kind of what type of, kind of that next level of data for San Francisco of what types of buildings they are, what type of real flaws they have once we look into the drawings, and cost of retrofits, because we're developing schematic retrofits and having them costed. So again, that's another important kind of piece of data, is to kind of figure out how much all this is going to cost, but understanding how many buildings we can afford to do and how much the collapse risk really is kind of that first step. And so that's one of the things we're working on right now, as these other great people in the room are working on the technical side of things. And so again, plugging the Concrete Coalition, we're looking for all the ideas and help that people are willing to provide. So talk to David Gonzalez about helping get involved with us, or if there's anything you can do to volunteer efforts, and just get ideas out there, because again, all these things are going on, but we're trying to kind of help inform, just kind of make micro movements as we move forward so that the policy can be kind of pushed in the right direction, knowing how big the problem is, start with the low-hanging fruit, so to speak, and kind of make positive progress.